Worksheet 5A and Part B. For Part B, the rectangular 3.2 by 6 inches and A36 steel column shown as shown here, and it pin at both ends, pins both ends for the rotation about x-axis. So as you can see now, they give the ends condition different for each direction. So pins at both ends for rotation about x direction, x-axis, and fix at both ends against rotation about y-axis. So what is the failure load if the column is made of steel, A36 steel, and it is a long or short column? So it's different from the first one. It pin at both ends for x and y direction, but this one is the end condition is different in x axis and also y about y axis. So when that is the case, as you can see, the P critical, the critical load pi EI over KL square, and the I for each direction are not the same for rectangle, and K depends on condition. So with that, we have to determine the critical load for bending about x axis and about y axis. So with that, we first find out the area moment of inertia for each axis and also the effective length factor for each axis. So that we have the cross section here is 3 by 2 inches and 6 inches, and we also consider the for this one we have the x is perpendicular to the 6 inches and the y is perpendicular to the 3.2 inches. So with that we can find out the area moment of inertia in x direction for rectangle. So it will be parallel time perpendicular cube divided by 12, and with that we will get this one a 57.6, and the unit is inch per 4, and IY direct area moment of inertia about y-axis. IY is equal to parallel for y here. By definition, it will be equal to 6 times 3.2 the perpendicular cube divided by 12, and that one equal to 16.38 in 4. So from that we also determine what is the critical load, what is the failure load due to buckling, and failure load or stress due to yielding. So let's work on the buckling. So for buckling, as I mentioned, because the support end condition, the end condition in x and y direction are not the same, and also the area moment of inertia for cross section are not the same in this case. So we have to determine the critical load for bending in x and y direction separately. So the first equation, we want to determine the critical load in x direction. So let's emphasize this one here, in x direction. So it will be 5 square E I x over KL square. So plug in 5 square for steel or that one, A36 steel, so it will be 29,000 KSI, IX 57.6 divided by KL square, K effective length factor. For about x-axis, it pins at both ends. So go back to our node. B, both ends are pinned. Effective length equal L and effective length factor equal to 1. Go back here. We can have equal to 1. And then L is 20 feet. Convert it into inches, so that one is 20 times 12 inch, and that is equal to 240 inches. Plug in here, time 240 inches square, and from that we have the critical load is 285 kips. What does that mean? In x direction, the critical load to make it buckling about x-axis is 285 kips. Similarly, we find out what happened. What is the failure load for buckling about y-axis? So critical in y-axis equal to pi e I y pi square k L square, and now it's pi square young modular same material steel IY 16.38 inch power 4, and K in that one. The top one here is K equal to 1. And if we go to about y-axis, the problems give us a fix at both ends against rotation about the y-axis. So from that, go back to our node for the effect of end condition. We want to find out K effective length factor. Fix at both ends, which is the D scenarios, and that is K in that equal to 0.5. So from that, here we can go to back to the equation that is 0.5 times the length also 240 inches and square, and that load is equal to 325 kips. 325 kips. So as you can see, in order to buckle about x-axis, it will be 285 kips. To buckle about y-axis, it's 325 kips. What does that mean? This column, it will be buckle about x-axis, smaller. From that, we want to check as its failure load due to buckling is 285 kips, whether it also yielding or not yielding with that load. So we will check for yielding, and for here we have the sigma actual when if the load 285 kips for buckling happen, what would be the normal stress in this material, in this column? So it will be P over A at the equation, and it fail about X. So you have 285 kips divided by A. So it equal to, for cross-sectional areas, it's 3.2 times 6. So with that get 14.84 KSI. What does that mean? The actual yielding, if it buckle about X, is 285 kips. The actual normal stress is 14.84 KSI compared to the yielding for A36 steel is 36 KSI. So here, as you can see, it less than the yielding stress, which is 36 KSI. So from that, what we can say, it's not yielding with the load 285 kips that buckle about x-axis. So what does that mean? We can say that for this column, it buckle before yield. And when buckle before yield, to be more specific, with specific in this case, it's the buckle about x-axis. And from that, we can say when the column is failed due to buckle over yielding. So this one is failed, the buckling is governed. So in that case, we can say that is a long column. And when it's long column, compared to the short column, as we say in the part A, so in this case, it's long column. And as you can see, the failure for this case, it P fail equal to the P critical in X direction, and that equal to 285 kips. 285 kips. So with that, we done for part B of worksheet 5A.